What is the biggest possible planet? How will we mine metal asteroids like Psyche? And will we ever see what's outside the observable universe? All this and more in this week's question show. Hey everyone, welcome to the question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. We also record this show live every Monday at 5 p.m. Pacific. So if you want to come and join the show live, you can carry on the conversation with other people, ask follow-on questions. It's a lot of fun. It's about double the length of this edited down version that you're watching here today. And there should be an event here somewhere on the channel. You can click to, I guess, get a notification when the live events are happening, and then you can come and join us. All right, let's get into the questions. Jason, what is the theoretical size of a planet? I've heard that planets will start to shrink if they get too massive. So what is the limit in size before they start to turn into a star? This is kind of cool. The largest possible planet is about the size of Jupiter. So Jupiter is about 11 times the size of Earth. Like if you put 11 Earths side by side, that is the size of Jupiter. And Jupiter is sort of at the theoretical limit of how big a planet can be. And that if you add more mass to Jupiter, it will actually start to make the planet compress down in on itself, smaller and smaller and smaller. Now there's a limit, of course, but still more massive planets don't get a lot bigger than Jupiter. So just to give you another example, like if you were to add 13 times the mass of Jupiter to it, then it would become a brown dwarf. And again, it wouldn't be any bigger than Jupiter, but now it would have such a dense core that it's starting to fuse deuterium. It would start to be generating heat inside its core because of this fusion process, and it would still remain roughly Jupiter sized. In fact, the TRAPPIST-1a star, this is the one famously that has like 7 Earth-like worlds orbiting around it. It is a red dwarf star, but it's only about 10% bigger than Jupiter. And so Jupiter is the same size as a star that has close to 100 times the mass that Jupiter does. And that just shows you that when it comes to planets, really Jupiter is at the very limit of how big a planet will become. And there are even red dwarfs that are smaller than Jupiter. So it'll be very strange, right? Can you imagine you would have like a Jupiter mass planet orbiting around a red dwarf star, and the planet is bigger than the star, even though the star is going to have 100 times more mass than the planet. I'm sure you've noticed this exoplanet name from the Star Wars universe pop up over my shoulder, and that is a way for you to vote on the questions that you thought were the best this week. And this week's one was a landslide, and that was for Can't Be Serious about whether humanity will have a powerful enough telescope to see an Earth-sized planet orbiting a sun-like star in the habitable zone. I feel like I guess I gave a good answer, but I know it's a very sad answer, which is that the answer is no, we don't. But if you haven't already watched that episode, we'll put a link in the show notes. You should definitely go and check that out. So with today's episode, watch through all of the questions, pick the one that you like the best, and vote down in the comments. Just type in the name of the Star Wars planet that you like the best. We'll count up all the votes and we will celebrate it next week. Fugal. How complex do the spacecraft need to be at 1000 AU to make use of the solar gravitational lens? We talked about this last week, that the way that we're going to be able to directly image an Earth-sized world orbiting around a sun-like star with the kind of resolution that makes us really feel like we're living in that science fiction future is with the solar gravitational lens. And this is where you fly a spacecraft out to about 1000 astronomical units. And at this point, the gravity from the sun acts like a natural telescope lens. But 1000 astronomical units is very, very far away. When you think about the Voyager spacecraft, Voyager 1, which is the most distant object ever sent by humanity, is at 159 astronomical units, and it's been flying since 1977. So if you want to be able to make that journey within a human lifetime, we're going to need methods of flying a lot faster. And we've talked a ton about this here on the channel. There's a lot of NIAC awards. There are various solar sails, mag sails. There are these strange pellet guns that will be able to fire material at spacecraft to accelerate them. You're looking at nuclear rockets, fusion rockets. There's a lot of great ideas to try and really dramatically decrease the flight time to get out to the solar gravitational lens. But still, it's going to be expensive. You're going to need a fairly large rocket with a very powerful way of getting out that far away from the solar system if you want to be able to do it in any reasonable amount of time. And so you have to pick your target really, really carefully. And we talked about this as well, that we're going to have to be absolutely certain which individual exoplanet we want to send a spacecraft out to be able to image. The size of the telescope actually isn't that big. You could have a telescope be about 1 meter across, which, 3 feet. So dramatically smaller than the Hubble Space Telescope. And even one that is smaller than that would still do a really good job. And so I think you're exactly on the right path here, which is that, we always talk about how TESS is the finder scope for the James Webb Space Telescope. Well, the James Webb Space Telescope is the finder scope for the Solar Gravitational Lens Telescopes, many of them. And so as various exoplanets finally meet a certain criteria for characteristics in their atmosphere, changes in their albedo as the planet seems to be orbiting, other trace detections that we can make, we will spin up these solar gravitational lens telescopes and start throwing them out to the solar gravitational lenses all the way across the solar system. Maybe you'll send multiple ones in one spacecraft so that they can work together to move to their various final positions if the targets are clustered in the same area. And so I wouldn't be surprised, there will be a time when we will send one, and then a few years after that we'll send a couple more, and then after that we'll send a few more, and it'll still be 20 years before the first ones start to arrive into this observation cone where they can start to actually see their targets. And over time we will have discovered more and more and more, and each time we find a really compelling new exoplanet, we will send another one on its way. And then we just have to be patient. But then as spacecraft get faster, as our propulsion systems get faster, we can get this weird situation where we're going to have these telescopes arriving at different times as our technology improves and as we are able to see more and more of the universe. So it feels like that is the future, that having these solar gravitational lens telescopes, the ones that give us that megapixel image, 1,000 pixels by 1,000 pixels, that is such a compelling vision for what the future of exoplanetary astronomy looks like, that it feels inevitable, that it's just a matter of time but as we work out the various technology and finally choose that target that we're going to send it to. Now, I've got a very long conversation about this technology with Dr. Slava Turyshev. He's the guy who developed the concept, received NIAC grants to be able to work on it, and we talk about this at length and hopefully answer most of your questions about this idea of the solar gravitational lens. So we'll put a link to that in the show notes as well. Baby Makar, on the topic of mining asteroids, how would you mine solid metal asteroids like Psyche, or would you just build a giant furnace and melt it down in one big chunk? I'm sure you've seen so many of these articles on the internet about how NASA is planning to send a mission to an asteroid that's worth, and then they just come up with some enormous number, right? It's 70 quadrillion dollars. It would make everyone on Earth a multi-trillionaire, et cetera, et cetera. And that is, I guess, true. But then if you brought that much precious metal back to Earth, and it would devalue all the metal and it would crash the world economy. And so it's not really that accurate. But the question you're asking is how would you get this stuff? If asteroid Psyche is just a ball of solid metal, how do you asteroid mine a ball of metal? And the answer is that it's probably not a ball of metal. It's a mixture of metal and rock and other stuff. And so we got some new images from asteroid Psyche within the last couple of years, and this helped sort of give a better sense of what the surface is like. And it's probably more mixed. So instead of just being this gleaming planetoid of chrome, it's, think about something that would look much more like many of the other asteroids that are here in the solar system. And it's going to have craters and pockmarks and all that across it. It's going to have lots of debris and rock on its surface, but it also clearly has the density to see that it still has a lot of metal, and maybe it even has like metal volcanoes or the remnants of metal volcanoes. So how would you mine it? I mean, the same way that you would mine any asteroid. You would land on the surface, you would set up your railgun on the surface, you would start to grab chunks that are just sitting there on the surface, plop them in your railgun, fire them off into space, and eventually you would have cleaned off the surface of the asteroid for anything that was easy to pick up. And then you are indeed left with metal. How do you extract metal? I mean, when you're really far away from the sun, like there are ways that you can concentrate the power of the sun. You can set up some kind of smelter to try and remove it, but it sounds hard. So probably they'll stop. Megavolt Meister, how do we detect magnetic fields outside of our solar system? Yeah, you've probably heard a lot of research where astronomers say we see magnetic field lines out there in the universe, and like, it's not like you're getting a magnet close to a giant galaxy cluster. How do you detect those magnetic field lines? And it comes through the particles. They're following along these magnetic field lines. As the particles are whipping around these galaxies, as they're whipping around star systems, as they are going around black holes, neutron stars, magnetars, they emit radiation. And so astronomers are able to detect the radiation that's coming from these particles and then use that to map back to actually figure out the strength of the magnetic field in various places that they're looking. One really cool idea is that astronomers soon will be able to detect exoplanets because of the magnetic field lines around these planets. We think about the Earth, right? We are surrounded by a magnetosphere, and that protects us from the sun. And as particles from the sun are streaming towards the Earth and they impact the Earth's magnetosphere, we get auroras. And from some distant observer, they're going to see the radiation that is coming off of Earth because of the interaction between the magnetosphere and the particles that are hitting the Earth. And so when you think about it, right, they are detecting the radiation, the auroras that are coming from the planet, and using that to infer that planet Earth has a magnetic field. And we'll be able to do the same thing. We'll be able to look at other planetary systems, detect that telltale signature of an aurora on a planet, and detect the existence of the planet at the same time that we also know that that planet is protected by a magnetosphere. It's just within our limits right now, but there are other telescopes coming that will be able to do that. This idea of putting a radio telescope on the far side of the moon, one that can see the longest wavelengths, that's the kind of target that we'll be able to pick up, as well as being able to peer into the dark ages of the universe and measure the magnetic field lines around. So mainly this work is done in the radio wave spectrum. If you like my answers to your questions, as well as the other things that we do at Universe Today, why don't you consider joining our Patreon club? This allows us to keep a minimum of ads for everybody. Like, as you can see, there are no ads during the middle of this video. As a patron, you also get an ad-free experience on universetoday.com for life. Even if you unsubscribe, you'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: John Tolles, Nolan Dwyer, Norman Gluckman, Shiram G, Todor Nakev, Grald, Modsu, Lynn Raymond, Judith Arnold, and Alf Badencourt. Join the club at patreon.com/universetoday. Kinetic Dyslexic. Do we know which space telescopes China has funded? I know one or two of the larger ones being built, they're funding. There are a lot of projects that are coming out of China, and I kind of struggle to keep track of all of the projects. I mean, they've got the largest radio telescope on Earth. They're building the largest steerable radio telescope on Earth. The one mission that I know a lot about is that they're planning on building their own space telescope, their version of the Hubble Space Telescope. So their telescope's called Shentian, and it's going to be a 2-meter telescope. When you think about Hubble, it's 2.4 meters, so it's going to be a little smaller than the Hubble Space Telescope. And the original plan for Shentian was that they were going to take this telescope and attach it to their space station. And so there would be some disadvantage to that, like it would be experiencing all of the vibrations on the space station, but then you would have all the advantages, like you could do spacewalks, repair it, swap out new gear, etc. And I guess later on they decided that wasn't the best idea, but it's going to fly in formation with their space station, and then it's going to dock to the space station whenever they need to make various upgrades. So I think it's a very clever idea. The other thing is that it's going to have a much wider field of view than the Hubble Space Telescope. It's going to be more similar to like the Nancy Grace Roman, which is also a Hubble class telescope. And it's going to be able to have this very wide field of view and help assist in the search for dark matter, dark energy, you know, the large scale structure of the universe to help figure out the evolution of the universe. I've seen a ton of papers where Chinese space scientists are proposing different ideas for space telescopes. We've reported on a bunch of them at Universe Today. So the Xintian is the big one that is in the works, but you know, depending on how many of these actually see space, there could be a lot of them in the future. Gamma Program Kid 56. Do you think they will ever discover the rest of the universe in the far future? When we look out into the universe, we are seeing all of the regions where light has been traveling from essentially the beginning of the universe to reach us. We call that the observable universe. And wherever you stand, you are at the center of your own observable universe. So you're watching this video and you're halfway across the earth from me, or maybe you're in the same country, I don't know. But you have your observable universe, this sphere that is centered on you, that you can look in any one direction about 46 billion light years, and you're seeing the beginning of the universe, because that's how long it's taken for that light to go from the Big Bang to you today. I have a different observable universe. We all have our own observable universe. The way I like to sort of think about it is if you're like wandering around in a very thick fog, right? That you can see your hands in front of you, you can see stuff around you, but after a while the fog gets very thick and you can't see far away. And yet I can be in my part of the fog, you're in your part of the fog. We're all seeing our own separate observable universes in the fog. And so when you think about it, like just objectively, there is more universe outside of my observable universe. There's more universe outside of your observable universe. And from what astronomers can tell, the actual universe is at least 1,000 times bigger than the observable universe that we can see. And the other possibility is that it's infinite. Like astronomers don't know if it's merely 1,000 times bigger than what we can see, or it's infinite. The point is that we can't tell, because essentially the flatness of the universe is so perfect that it rules out anything that is smaller than about 1,000 times in volume than what we can see with the observable universe. I guess the question that you're asking is like, can we ever know anything about the rest of that universe? And we could do better and better observations at the curvature of the universe, and we could push that minimum size up. So we might like really precisely measure the flatness of the universe and get to a point where we say, okay, the universe is at least 10,000 times bigger than we know, or 100,000 times bigger than we know. But we can never visit it. We can never go beyond the observable universe. In fact, we can't even get to the observable universe that we can see. 96% of the universe is already moving away from us at the speed of light or faster. And so even if we left today at the speed of light, we could only reach a sphere around us that accounts for about 4% of the observable universe. And so not only can we not find out what's going on outside of the universe that we can observe, we can't even reach the universe that we can observe, which is kind of sad, but it's just that's what you get when things are just gigantic, possibly infinite. Steve Wilbrandt, Oumuamua, artificial or natural? I don't know, but like most likely it's natural. I mean, when you think about all of the possibilities out there, Occam's razor tells you that it's just got to be a rock, or a rock with ice on it. And I know that Avi Loeb will disagree with me, and he is a Harvard astrophysicist who knows a ton, and so obviously I'm not going to have a straight up argument with him, but I just sort of like my experience in watching as interesting new discoveries eventually become more and more mundane when people finally figured out what it is that they are. The most recent thought is that it was formed far out in whatever solar system that it came from, and it was able to escape into the universe, and then it was bombarded with hydrogen atoms over the millions or billions of years as it was floating through space, and all of this hydrogen kind of compacted onto the outside of the object as it made its way through space, this hydrogen iceberg. And then as it approached the solar system for the first time, this material started to outgas in a unbalanced way. So instead of it sort of outgassing in all directions, it outgassed in a way that changed its acceleration in surprising ways. And according to recent calculations, this is within the possibilities of what hydrogen outgassing could do. So like hydrogen outgassing seems like a more feasible answer to me than it's aliens. And don't get me wrong, right? Like I never shut up about von Neumann probes that are traveling from star system to star system. And I would love for it to be some kind of alien probe that's sent to the solar system to learn more about us and maybe to share its technology. Although now it's leaving us, like it's not sticking around, which is kind of rude. So no, I feel when you look at all of the interesting things that have been found, Boyajian star, was it some kind of Dyson sphere surrounding a star? Nope, just dust. So it just feels almost certain that this will turn out to be something that's completely natural, that when we do find some kind of result of intelligence, it's going to be very obvious, and it will be, there will be a lot of argument about what it is. Donovan Smith, is it possible for a planet to be caught in the Lagrange point of a binary star system and so have the stars rotating around the planet? All right, I had to read this question a couple of times to sort of wrap my head around what's going on here. So you've got a binary star system. You've got two stars that are orbiting around a common center of gravity in between them. And so both stars are rotating this empty spot in space. And then you're asking, could you put a planet at the middle of this empty spot in space and then have the two stars orbiting around it? And it would feel like you are at the center of the star system. And so the heliocentric model of the star system would be wrong. It would be the Earth-centric or the planet-centric. And that sounds really cool and really exciting. It sounds like a really cool science fiction story, but no. And the problem is that position would be unstable. And so back to the Lagrange points, right? When you think about, there are 5 Lagrange points around every 2 objects with vastly different amounts of mass. So if you have a object with the mass of the sun and you have an object with the mass of planet Earth, then there are 5 Lagrange points. 3 of them are lined up between the star and the planet, and they are unstable. They are like sitting a rock at the top of a tall mountain, and any kick pushes the planet off of the rock, off the top of this mountain, it's going to roll down faster and faster and move away. And so when you think about all the spacecraft that we have positioned at the different Lagrange points, say James Webb, which is at the L2 point, it has to use propellant nonstop to maintain that position. And as soon as it stops using its propellant, it'll start to drift away from the Lagrange point. Well, you would have this same situation. You've got these 2 stars and they're orbiting around each other, and they're not going to be exactly the same kind of mass. And so this balance point in between them is going to shift and move around, and the planet isn't going to be able to stay in that shifting moving plane. So it's going to drift out, and eventually it's going to hit one of the stars. But you could have planets orbiting around binary star systems, but they have to be orbiting. So there's 2 scenarios where this is possible. One is you got the 2 stars that are relatively close together, say a couple of astronomical units away from each other, and then you have your planet orbiting both stars, and it has to be like a factor of 5 beyond the distance between the 2 stars together, and then you can have the whole thing be stable, and the planet will just orbit around these 2 stars, which would still be pretty great. I mean, you'd look and you'd see the stars would be sort of in the sky. Sometimes they would be lined up, and sometimes they'd be far apart, and they would just be kind of doing this. The other possibility is that if the stars are really far apart, then your planet can orbit one of the stars and not be completely disturbed by the other star. And so then I guess the question that you're asking as well is like, could you get Lagrange points from a binary star system? And the answer would be yes. So if you had your two stars orbiting one another in this binary system, and then you had a large planet far away from them, say a Jupiter or whatever, to the point that it was stable, then you would end up with those same 5 Lagrange points. One that is in between the binary stars and your Jupiter, one that's on the other side of your Jupiter, one that's on the other side of the two stars, as well as the two that are forward and backwards in the orbit of the planet. But because these two stars are whirling around each other, the shape of these Lagrange points are going to change dynamically depending on how the stars are lining themselves up. And so you might end up with either a very large point that isn't like a pinpoint gravitational balance, but is this sort of gravitational blob where you can kind of stay in the region. And same thing with, say, the L4 and the L5. They're gravitationally stable. They're like the opposite. They're like a valley that you can get into and you sort of hang around inside of there. But then I wonder, right, if you had the two stars orbiting around each other, depending on how far away they are apart from each other, how away from your planet is, they might actually cause those Lagrange points to be unstable again. So it's an interesting question. It's not a Lagrange point question that I've had before. So I'll just add that to the list. Prismla Legian, what is your take on artificial versus organic intelligence? I don't think there's anything special about organic intelligence. Like, we are the result of hundreds of millions of years of evolution here on Earth, evolution through natural selection. And natural selection sort of made the brain, and this is how we got our intelligence. But it wasn't the plan. It was just that our ancestors were able to survive in their environments better. And everyone who's watching this, right? All of our ancestors survived long enough to be able to produce offspring. And we are the result of that. And so there are all kinds of ways the human brain has got problems. And there doesn't feel like there's anything special. Like, we have a computer made of meat in our skull, and it's amazing what we're able to accomplish. And thanks to hundreds of millions of years of that evolution. When you look at computers, I don't see why we wouldn't have artificial intelligence that is the equivalent or vastly beyond what human beings are capable of. It's like, there's nothing special about our meat computers. They're just the ones that we ended up with. And there are probably dozens of different ways, hundreds, thousands, millions of ways that intelligence could arise in different configurations. Humans being one form, artificial intelligence being another form, some other life form on some other world being another form. And I think, like, we perceive the world from the perspective of being intelligent creatures. And we can't imagine something that is more intelligent than us, that isn't us. But that doesn't mean that it's not possible. And so I think that we're about to find out what it feels like to share planet Earth with something that is as intelligent or more intelligent than us. And I hope we can figure out how to remain friends. Joe Conrath, what is your preferred answer to the Fermi Paradox? I think we're alone in the universe. I think we are the only intelligent civilization potentially capable of spaceflight in the universe. Not only that, but I actually think that we're the only life in the universe right here on planet Earth, that there's no other place in the entire observable universe that life has formed at all. That's my preferred answer. The alternative answer being the great filter, that all life, when it reaches a certain point, gets wiped out. It's just so horrible that I don't like that answer. So I'm going to go with we're alone, or we're first. That's okay too. We are the most advanced species in the universe so far. All right, those are all the questions that we had this week. Thank you, everyone who asked questions in the chat, everyone who showed up for the live show on Mondays, 5 p.m. Pacific time. Don't forget to vote, and we'll see you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to David Giltonen, Modsu, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.